Hello there, and welcome back to another PCG tutorial. It's been some time since the last video. Lots of people want to use PCG internally and externally, which is awesome, but also adds more workload. Hence why there was no video in the last 8 months. But I managed to find some time to dive a bit more into one of the new and hottest topics of PCG, GPU execution. I plan to make a small series focused only on GPU. You probably saw the State of Unreal at Unreal Fest Orlando, where the Witcher 4 tech demo was presented. Most of the foliage is spawned at runtime on the GPU with PCG. The GPU in PCG is available since 5.5, but a lot of optimizations to be able to ship the demo were done in 5.6. So this tutorial will be on version 5.6, even if what I'm showing you today should in theory be feasible in 5.5. If you want to see what is feasible in 5.5, you can check out the Cassini demo presented at Unreal Fest Seattle. And it's not even a forest. For all the external resources, you'll find the links in the video description. Be aware though that GPU execution in PCG is still experimental and very advanced, as you won't be able to just turn on GPU mode on some nodes and magically it will be better and faster. GPU nodes mostly rely on HLSL code, so you have to know the basics of HLSL to fully harvest the power of GPU in PCG. Don't worry, we'll definitely know that it is a big barrier of entry, so in future releases we'll make sure to port more and more classic CPU nodes into GPU nodes, so that they can be used without HLSL. In this episode, we'll have an introduction to GPU nodes. What are they, how we can enable CPU nodes to be executed on a GPU, how to configure custom nodes with the pins and access the data, and most importantly, what it means to have GPU nodes in your graph and the optimization that needs to be done, and what are the limitations. This is a bit of a preview of what we're going to do with this runtime generation where all the meshes are pushed through GPU nodes. I'm assuming you are familiar with runtime hierarchical generation, as I'll use it extensively in this episode. If you are not, I suggest you to go back watch episodes 7 and 8. GPU is a big subject, and I'm by no means an expert on HLSL or shaders, so I might not have all the answers to your questions, so don't hesitate to join the Discord server Unreal Source to ask questions. Also, as always, you'll find the project file on my GitHub page. All the links will be in the description. Also, don't hesitate to check out the documentation regarding GPU. Our doc team poured a lot of efforts to get an extensive doc for this, and it is a very good reference to come back regularly. Lots of things to discuss, so let's dive right into it. I'll create a new open world map, same as previous episode, and create a new graph, and name it landscape scattering. I won't reinvent the wheel, and we'll do usual, sampling the landscape and spawn some meshes. In 5.6 there are new shortcuts, like you can keep the button L and press and click to get a get landscape data node. You can check the list of the shortcut in the plugin folder and even add your own. In your engine installation folder, you'll find an engine plugin PCG config, editor per project user settings.ini. You can see all the nodes that have a shortcut, you can change them or even add new shortcuts. In the editor, 1 plus click create a double constant, 4 for vector 4 constant, S for get spline data, M for a static mesh spawner, etc. So in my case, I want to sample the landscape and spawn some meshes, so a surface sampler, and then drag plus M to automatically connect to a new static mesh spawner. I will select a mesh and drag the graph into the world, and I will make it bigger. Let's profile the graph. If we select a volume, open profile, and Ctrl plus click to get a full region without the cache, we get a PCG execution time of 10 milliseconds. That took 23 milliseconds real time between start and finish. And you can see that the static mesh spawner is taking most of our time. Enabling GPU in this case is very easy. You can just click on execute on GPU in the settings. And now you can see that the total time is 4 milliseconds. But we don't have access of the real cost of the static mesh spawner. That's the first limitation of the GPU, we can't profile the nodes individually. The result is identical, but the meshes are spawned directly from the GPU. You can see that the component on the actor is not the usual ISM, but a PISM, which is a lightweight CPU component that doesn't hold the instance data like the ISM does. But it also means that if I save and reload, the meshes have disappeared. That's another limitation of the GPU spawning. To understand exactly why, let me explain what's the difference between the static mesh spawner on the CPU and on the GPU. On the CPU, all the transforms of all the instances are first set on the ISM component, then the ISM will push data to the GPU scene to be rendered. But it can also update the wall for navigation or physics with collisions. While the GPU version is straight pushing the instances to the GPU scene, no representation on the CPU. And this brings us to another limitation. Since there is no CPU representation, the instances are not saved, and so they are lost when we reload the map. And no CPU representation also means no collisions or navigation update. When you decide to spawn on the GPU, it is very important to take this limitation into consideration. GPU spawning shines when you do generation at runtime of non-interactable meshes that have no collisions, meaning it is perfect for grass generation and microscattering, but won't work out of the box if you need to interact with those meshes like cutting grass. Still, you can definitely see that the GPU spawning is more performant than CPU spawning, and the more instances you have, the bigger the difference is. So let's switch to runtime setup. If you remember episode 7 and 8, we set our component to be generated at runtime, partition, and enable IGen in the graph settings. Don't forget to enable Treat Editor Viewport as generation source in the PCG world actor to be able to see the generation in the viewport. Let's push the system to spawn more stuff. I'll make the volume cover the landscape and increase the density of the sampling. And let's go back to CPU spawning to see the performance. Yeah, it's pretty bad. If you go back to profile the graph, you can see that each cell is taking a lot of time to generate, with the static mesh spawner taking a lot of time. So let's re-enable GPU. And yeah, you can see that it's way better, but we can still see the hitches, because most of the processing is still done on the CPU. Like the surface sampler is still taking 20 milliseconds per cell. Let's see how we can move the full graph to be executed on the GPU. I introduce a new node called the point generator. It generates a certain amount of points, in this case 256, that is static and can be overridden. Since it's empty, if you inspect the result, you can see 256 points that all are at the origin. Let's disable the CPU spawning for the moment. That's where we're going to be a bit more technical and actually code. If you don't see the HLSL source panel on the node, you have a button to open it. In this panel, you can see 3 sections. The first section is the declarations and can be modified. This is everything that is defined for you and can use. For example, you can see that the constant num elements gives you the number of elements that will be generated. If I change the value to 512, it automatically updates the declaration. There are a lot of declarations, I won't go over all of them right now and will present them when I'll use them. The second section is the shader functions. It is to define custom functions for your shader to tidy the code. Be careful to not write your processing code here, as it won't work. The processing code needs to go into the third section. In the first section, you write the processing code. This code will be called n number of times, once for every element, and processed in parallel. Which means that you can't have sequential logic, like place point A and then maybe place point B. Each point is processed in its own bubble and can't see what is going on the other points. Let's start with a very simple example, a 2D grid. There is already a function for that called createGrid2D. Contrary to what you would expect when doing CPU computing, this function is not returning an array of points, but just a single point. You can imagine as if we have a 2D grid of 512 cells, and the processing code will be executed for each of those cells. The function createGrid2D will return you the position of the cell you process for a given processing element. First thing we want to get the position of this point on the grid. So we create a new float-free variable, position, and store the results of the createGrid2D function. The function needs 4 values. The first one is the index of the element to process, and this is given by the variable element index. The second one is the number of points in total. This is given by the constant num elements. And the last two are the bounds min and max of a grid. Since we want to generate a grid within our runtime cell, we can use the function getComponentBoundsMin and getComponentsBoundMax, which will return the bounds of our partition actor. Now that we have our position, we want to write this information in our output point. For this, we use the outSetPosition function. Out represents the name of our output pin. If I change the name of the output pin to outPoints, for example, it becomes outPoints set position in the declaration. This takes 3 values. The first one is the index of the data to write to. This is provided by outPoints_dataIndex. The second one is the index of the element in the data. This is again provided by elementIndex. And the last one is the value to write, the variable position in my case. If I inspect the node now, you can see that the position is updated. Though in this case, the Z value is way below the landscape. For now, let's just hardcode it to 256. So I can add a new line, position.z equal 256. And we can see that in the inspection. If I debug my node, you can clearly see a perfect grid. But a perfect grid is definitely not natural. If I have those 4 points, we want to nudge them a bit, meaning that for each point, we want to generate a random displacement. For the first point, it could be this, for the second, this, for the third, this, and for the fourth, this. Which gives me those 4 points. And if I erase the initial points, you can see that we have a nicer random pattern. So how do we do that in practice? You can do randomness in GPU nodes, but the same way than PCG, it needs to be deterministic randomness, so that every time you generate with the same seed, you get the same result. If you didn't know, PCG is usually computing the seed for its points using the position of the points. You don't have to do the computation yourself though, there is a function for that, compute seed from position, that takes the position. And we can store the result into a uint variable named seed. On top of that, nodes that do randomness in PCG are also using the node seed and the component seed. All 3 different seeds are combined together to get the final seed. To get the node and component seed, you can call the getSeed function. And to combine both seeds, we can use computeSeed function. So we combine the results of getSeed and outPointSeed and store it back into our seed variable. Then we generate a random number based on the seed with frand. This will generate a random floating number between 0 and 1. To quickly see how this works, let's multiply the z value of our position with this value. This will randomly place the points between 0 and 256 in z. And then you can see that they are displaced now. We want to do the same, but on x and y. For that, we need to define, like in transform points, what are the mean and max displacement values. I'll choose 500, meaning that my points can be randomly displaced by up to 5 meters on x and y. You have access to the lerp function in HLSL that does a linear interpolation. So we'll generate 2 random offset for x and y that go between -500 and 500, and the alpha parameter is a random value generated with frand. Note that the seed will change every time the frand function is called, so I'm not generating twice the same value. I'll remove my random displacement on z and add the random offset for each axis. I have weird values there. That's because I have the max displacement that is an unsigned integer, and minus unsigned integer will give me a very big number, so it needs to be a float. Now you can see that we have a nice displacement, and it looks a bit more like what the surface sampler is usually producing. Don't hesitate to pause to understand those concepts. It's very important. Talking about the surface sampler, let's see how many points are generated in our setup. Close to 85k, and the points extent is 7. So let's crank our numbers to 85k and set the bounds to -7 and +7. Same as position, we use the outPoints setBoundsMin and outPoints setBoundsMax function to set -7 on the min and 7 on the max. And this gives us nice and tight points. But the Z position is still hard-coded, and we need to make them fit onto the landscape. The landscape is accessible on the GPU to query the height and the normal, and other things in 5.6, but we'll talk about it in a future video. For this, we need to add a pin to read the landscape. On the node, we add a new input pin, make it of type landscape, and name it landscape. You'll notice that the pin is automatically converted to a single input pin. That's because we only support reading for a single landscape. Let's plug our landscape and see what changed. In the declaration, we can now see that there are new functions to get the height, normal, and the base color at a given world's position. Let's start with the height. Instead of hard-coding the value to 256, let's use the results of the landscape. We use the function landscape_getHeight, and make sure to use the position after the displacement. And now it nicely fits the landscape. But if I go to the edges and make my volume bigger, you can see that we have points that float outside of the landscape. That's because the getHeight function is still returning a value even if it's outside of the landscape, and the value is the height at the edge of the landscape. But we want to make sure that we are not spawning points outside of the landscape, so let's add more information. From the getLandscape data node, we can get its bounds. The results is an attribute set with two attributes, boundsMin and boundsMax. And we want to send that information to the HLSL node. For that, we just add a new input pin of type attribute set and name it landscape bounds. As you can see, it again updated the declarations. Now we have this new line. It's the syntax to access dynamic attributes. In this case, I have two attributes, boundsMin and boundsMax. There is just a single data with a single value, and both attributes are of type vector, so float-free. In this case, the type would be float-free, and the function will be called landscapeBounds_getFloat3. So in my case, I want to get the boundsMin and boundsMax of the landscape. Use the function landscapeBounds_getFloat3. As a reminder, landscapeBounds is the pin that we want to read from, and float3 the type we want to gather. It takes three values. The first one is data index, is the index of the data. We just have a single data here, so we'll use 0, first index. Then we'll have the same thing for element index. We only have a single value, so it will be 0. And finally, the attribute name will be boundsMin in single quotes. And we do the same for max. Now that we have our bounds, we want to discard any point that is outside of bounds. The condition is that the x and the y coordinates are within boundsMin and boundsMax. It means that if the x position is less than the x boundsMin or greater than the x boundsMax, we should discard the point. And it is the same for the y-axis. The double straight line is the OR operator for Boolean operation. If any of those are true, we use the outPoints_removePoint function that is the equivalent of returning false in the point loop body in a custom blueprint element. We remove the point and exit the processing with a return statement. The arguments are the same than the set functions, it's the data index and the element index. And now we have a nice cut at the end of the landscape. Alright, we have the right height now, so let's spawn some meshes. Let's just duplicate the static mesh spawner node. And ta-da! I can now fly very quickly and it doesn't break a sweat. But my grass still feels a bit too similar. Let me add a transform node before the spawning for more variety. It doesn't seem to work. I have the same variation everywhere. That's because if you inspect the results of the custom HLSL node, all the points have the same seed. And I stated earlier, it means that all our points will generate the same random values. Let's change that in the HLSL code with outpoints underscore set seed using the seed we computed. Now we have different seeds per point. And it works, we have different scales and different rotations. But now if I fly around, the performance is definitely not good. What happened? If I go back to my graph in 5.6, you can see that there are some yellow arrows on the nodes. Those arrows indicate when there is a transfer between CPU and GPU. Down arrows means GPU to CPU, and up arrows means CPU to GPU. As you may know, CPU to GPU transfer are very slow. So every time you need to get the data on the CPU from the GPU, you have to pay the cost to read that data back, which can really hurt performance. And that's a big information to keep in mind. When doing PCG with GPU, you have to make sure that you are designing it with GPU in mind, meaning that you should avoid data transfer at all costs for a high performance setup. Each group of nodes that are GPU only will be grouped together for the execution and will be very fast. But adding a CPU node in between will force a readback and it'll be bad. In our case, it means that we can't use the transform points node, as there is no GPU implementation yet, unfortunately. We'll have to do it by hand. For the scale, it's going to be somewhat easy. It is the same as the displacement. We'll do a random linear interpolation between 0.5 and 0.8. Then I set the scale of my point with outpoints underscore set scale. So you can see that the scale is randomized now. And I get the performance back when I'm flying around. For the rotation, it is way more involving. In 3D, rotation is often represented as quaternion. Quaternions are a set of 4 floating values. In technical terms, there is a real part and 3 imaginary parts. You don't have to know how to write a given quaternion. You can use the library provided by PCG. You can find it in the PCG content folder in Compute Sources. If you double click on it, you can see all the functions. And we want quat from axis angle to create a quaternion from an axis and an angle. Coming back into our node, we'll generate a random angle between 0 and 360 degrees. But quat from axis angle requires the angles to be in radians. 360 degrees is 2 pi radians, and 2 pi is approximately 6.2832. Now we call the functions to get a quaternion. The axis will be z up, so a float 3 with 0, 0, 1. And same as position and scale, we set the rotation. If we inspect the node, we definitely have a random rotation, and we can see it in the world. Phew, the difficulty has definitely risen. We'll try to provide GPU implementation of nodes such as the surface sampler and transform points in the future. But for now, we have to do a lot by hand. Especially if you want high performance, you should try to do as much as you can on the GPU. In future videos, we'll see how we can use texture instead of a grid for the generation and how we can replace the landscape grass system with PCG. As a bonus, I want to introduce 2 more concepts, but this is pushing the difficulty even higher, so don't hesitate to stop here and digest while you learn there, before going into the next section. The first thing I want to show is how we can have some kind of gradient for generation distances. So we can have sparse meshes far away and denser meshes up front. You notice that the code is part of the node, which means that if you want to do another scattering elsewhere, you have to copy the code. And a good programmer will say that copying code is very bad. If you have to change the code in one node, you'll have to change it manually in all the nodes. Fortunately, in 5.6, there is support for sources as assets. So we'll convert our existing node to a source asset. You can create a new asset under PCG Advanced PCG Compute Source. I'll name it CS Landscape Scattering. And then copy the code of the node into it. And on the HLSL node, we can use the kernel source override to provide the source code. Now I can duplicate my HLSL node, and for each of my HLSL node, I'm going to have a different grid size. I'm going to use the 256 meter grid size for the first one, and 128 for the second one. And I'll also duplicate the static mesh spawner. And not forget to plug the landscape bounds. And finally, changing the seed on the second node to have a different random pattern. And now you can see that close to the camera you have a lot of meshes, and farther away you have less meshes, but you still have some. Since I'm close to the camera, I have both grid sizes that contribute to the meshes. I can reduce the number of points generated by the smallest grid size. We'll still have dense generation close to the camera, but farther away we still have some meshes. Finally, we have the issue that the grass sample is not following the normal of the landscape. It stays up. Unfortunately, this part is pretty complex, as we don't have a built-in method to convert a normal vector to a rotation. So we have to make our hands dirty. Basically, what we want to do is reproduce the behavior of the surface sampler that changes the rotation from the normal of the landscape, and combine it to a random Z rotation for diversity. But we have to do everything by hand. I won't explain the underlying equation for that. That's out of scope of this tutorial, so we'll take those for granted. In our case, we want to create a quaternion that represents the rotation to align with the normal of the landscape. I'll take the function from the template graph that is available in the PCG plugin content. In the folder Graph Templates, templates showcase runtime grass GPU. And the function we want is in the point generator under the shader functions quat from normal. This constructs a rotation matrix for the normal and convert the matrix to a quaternion. Since it is a utility function that could be useful later on, I'll create a new compute source called CS quaternion utils and copy my functions there. Back onto my landscape scattering HLSL code, I add this util source as an additional source for these functions to be available in this file. Now we can extract the normal of our landscape at the point's position. Same as height, but this time with landscape underscore get normal. And use my new utils function to make a quaternion out of it. What's nice with quaternions is that you can multiply them to combine them. If I have a quaternion that represents a rotation around the x-axis of 45 degrees and a quaternion of a rotation around the y-axis of 45 degrees, multiplying the two will give me both rotation applied one after the other. Multiplication order is important. Quad A times quad B is usually not the same as quad B times quad A. For the multiplication, we're going to use the function quad multiply. In my case, I want to first align the point with the normal, then rotate it around Z. The order is right from left, so on the left I'll have the second rotation, the random rotation, and on the right the first rotation, the normal quaternion. And now you can see that the rotation is correct and following the landscape. Alright, this was a long introduction to GPU in PCG, with increasing level of difficulty to have something similar to the CPU path. But the performance difference is enormous. We saw basic concepts to enable GPU on existing node that supports it, like the static mesh folder, and the limitations that come with it. We also saw how to write our own HLSL node to generate points, sample the landscape, and read attributes, and do some randomness with a lot of hands-on math. We just scratched the surface of what we can do with GPU in PCG. It is definitely not limited to point scattering. You can imagine running physics simulation, texture sampling, etc. But it is going to be for a future video. I hope you enjoyed this video, way more complex than the other one. Don't hesitate to experiment with it and ask questions on the Discord. That's all for me for today, and I hope to see you in the next one. In the meantime, have fun with PCG. Take care.